as a matter of fact, let's see. Here we go. Let's do this one. Let's see, snippet. Go over here, add a page, drop it in there. It says a 5 pound collar is released from rest at A, travels along a frictionless guide, which is good for us. Determine the speed of the collar when it strikes the stop down there. MGH1 plus. There's no spring. Yeah, what am I saying? There is a spring. 1/2 K delta squared plus 1/2. Okay, I already wrote that. V squared over 2. There is, but I'll include it. There's no friction equals to MGH2 plus 1/2 K delta 2 squared plus 1/2 MV2 squared. Started from rest. That's gone. Let's put our datum down here. And so MGH is 5 pound collar. That's MG. MG is equal to 5 pounds. The H, 1.5 and then 1. What is that? 2.5? 2.5. So that's the potential energy of this thing sitting up at A. Okay, the string's unstretched length is 1/2 of a foot. So 1/2. The spring stiffness is K. Oh, I mean, a little 4. Then it's 1/2 a foot. So that means with that and that together, the stretched length is 2 feet squared. So it's unstretched down to here, and then those 2 feet, it's stretched, equal to MGH is 0, so that term is 0, plus 1/2 K, K. Yeah, it's still the same. Yeah, 2, 4. Yeah. And then the delta, okay, so from here to here is 1. So I think we're looking at, it's still halfway stretched. And then plus 1/2. The mass is 5 over 32.2. That's the slugs. V2. So let's see. This, okay, 4. Okay, so take away one of those, and then this number should give me 8. And then 5 times 2.5 is that 12.5? Is that right? So 20.5? Am I right there? I may be wrong. Okay. And then I got this other side, that thing. Okay, I'm going to have to break out the calculator on this. Let's see. 0.5 times 0.5 times 4 divided by 2. Oh, that's it, 0.5. So it took off that 0.5. So I got the right number there? Okay, so now I got this funny thing. All right, well, I'll leave it. I'll leave it like here. And then I'll say V squared. Okay, so I can move this over and knock out that. So I got 20 times 2 times 32.2 over 5 and take the square root. Maybe I've got the ability to do that. Okay, take the square root, and I get 16. That's good enough. 16. So V is equal to around 16. So it's really that simple. These problems are incredibly simple. Here, let me check the back. Okay, F 1416. Nope. 14. Is the F's before these? 14. Yeah, it's got these. Yeah, was it 14? Okay, 16. So what you'll find is once you do a few of these and just recognize a few of those things, it really works itself out pretty easy. They're not, the only thing that catches you is possibly the geometry that he might throw at you. I don't even know what page I was on. Well, that's close. No, wait, no, now I'm not close. Oh, here you go. A 17 or 75 times the initial rate. Determine the required unstretched link electrically attached in order to stop on just above the surface of the water. Shall we do that one? That seems like there's no answer in the back of the book, but it seems entertaining enough and appropriate based on our conversation there. Well, that's probably true. Unless he was a small ant man. Here, well, yeah. So here we go. 75 pounds. Okay, so let's start this up. I guess this is at the last section. Okay. So he jumps at the bottom. We carry at the, jump at the top, carry at the bottom. Okay, it's 150 meters. MGH plus 1/2 K delta squared plus 1/2 MV squared. There's no extra F dot D, so I'll save myself the space of putting that in there. MGH 1/2 K delta squared plus 1/2 MV squared. Okay. Oh, okay. So the bungee jumps off with an initial downward speed of 1.5. Okay, so he had to do that to me. 75, 1.5 squared. Well, ironically, it doesn't matter. Yeah, that's the cool thing. Okay, so I'm assuming that the bungee cord, somebody's holding it, so it's not stretched. Determine the required unstretched length of this, which he has attached. Stop momentarily just above the surface. The stiffness of the cord is that. Oh, he wants to know the length. Okay. Well, the length is going to be part of the delta. Okay, the MGH, 75 kilogram person, 9.81, and then 150. So I'm assuming when he jumps, somebody's holding it. It's not stretched at all. Then I get over here to this side. This thing is 0. The whole kinetic energy is 80 delta squared, and there's nothing here. So I get this and this is equal to that. Problem is with this is interesting. Okay. You know what the problem here is? Well, let's find out what delta is first. Okay, so I think I can do all those numbers. They're not terrible. 1.5 times 1.5 times 75 divided by 2. Well, it's a funny number. 84.375. 150 times 9.81 times 75. Wow. That is a big number. So really, who cares whether you jumped off? Okay, so let's add it anyway. Oh, I forgot that, didn't I? Yeah, so I got to get my 80 over 2 and then squared. So I got to divide that by 80 or just divide it by 40. How about that? Divide that by 40 and then square root it. 52, 52.50, 55. Yeah, I guess, but after you slip that under there, and then, so I think the key is that's how much it deflected. So that means it went down and finally popped, and then it stretched to here, which is 52.55, and that's 150. So the unstretched length, yeah, 150 minus 52.5. Okay, 97.45. Okay. So I'm hoping that they do things like that. I mean, I'm not about to go do that stuff, especially after that video the last class showed me. I'm not doing that. So, but it all comes back to this. I mean, this stuff is, when you realize all you're doing every single time is this equation every single time. And you include that. In this case, it wasn't there. So you include that like right in here, say. And it's always the same. And so all you have to do is do an accounting. You know, what's the potential energy? What's the potential energy of the spring? What's the kinetic? Did I lose or gain any force or energy because of a frictional force losing or pushing a force, you know? And then the final state. And that's it. So all these problems are really, once you identify all of those terms, it's pretty easy to do them all. And you could work problems in this section that would just be impossible in that chapter 13, but in 14, they're easy. So here's one. See, 10 released from rest when theta is equal to 0. The tension of the spring is 100. Determine the speed of the neglect the mass of the rod and the size of the sphere. Okay. Tension of the spring. Okay. Okay, so that's a tricky one. Tricky, but not terrible. There's little verbiages you got to kind of pick up on. Here, let's add a page. Okay, so what he's done, he's tricked me here. So at theta is equal to 0, the tension in the spring is equal to 100 newtons. But this is that. So this means, let's see, when it's 0, excuse me, okay, tension or force equals to 100 equals to K times, say, delta. But K is 500. So delta is equal to what? What is that, 0.2? Is that 0.2? So it's been stretched to 0.2. So this point, say this point swings up here. It goes to there, goes out here. So the triangle looks like this, 0.4, 0.3. Aha, I like this guy, 0.5. So delta is, the unstretched length is back here. So this is 0.3, and this is 0.2. Then he says, determine the speed of the sphere at the instant where it was, straight up and down. So straight up and down, the thing down to here would be 0.4, and then another one would be 0.3. So the stretched would be, total stretched, the 0.7, right? 0.4 and 0.3. But that's the total length. That's not the stretched part. That's the total length. The delta at state 2 then would be 0.7 minus 0.3, right? Should be 0.4. So delta 1 equals to 0.2. Delta 2 is equal to 0.4. So now I can just haul off and do this. MGH 1 plus 1/2 K delta 1 squared plus 1/2 MV1 squared equals to MGH2 plus 1/2 K delta 2 squared plus 1/2 MV2 squared. Did he say it started from rest? Released from rest. Hey, what's the, oh, it's a 10 kilogram. Okay, so now, here, I got to do that so I can go down. So what do I got? I got 10. Okay, so I'm going to make my datum all the way down here. So that means this term is 0. Did I release it from rest? I released it from rest when it was at 0. Theta is equal to 0. So that means the H is the distance from here to here, because this point is down to here. Oops, mistake-o. This is where I'm at. This is where the mass is. So the datum is not to there, it's to here. So the initial height, okay, 9.81, the initial height is from here all the way to here, because when it's vertical, the mass is here. That and that add together to give me 0.45 plus 1/2 K of 500 delta 1 of 0.2 squared released from rest equals to 1/2 500. This time it's 0.4 squared plus 1/2 mass of 10 V2. I think I got everything. Okay, so now the question, did I forget something? Okay, so let's see. Calculator, come on. Okay. Okay, let's start. Okay, 10, 9.81 times 0.45 gives me this number being 44.145 plus 500 times 0.2 times 0.2 again, divided by 2, 10 equal to, this mess is 0.4. Did I forget something? 40 plus 5. So move that over, it kills off that, I get 14.145. Oops, then I got to divide that by 5 and take the square root. 14.145 divided by 5, square root it, and I get 1.68. Now I did that so fast I don't trust it. Okay, so it's 1493. Okay, so 1493 on page 216. I realized I can leave that on there. See, oh, what happened? Did I jump right past it? Wait a minute. What's going on here? That's 20. Okay, I'm really confused. Where's 1493? Wait. Did I pass it? Oh, okay. Is that what I got? All right. And I ran you over 2 minutes. So you start to see how complicated they look at initially, and they're not. You just have to work your way through the geometry and stuff. So we'll call it a day, and we'll all go home. Or back to the dorm or wherever.